used to be my pleasure for a number of times, and it's my pleasure again to come here. Yes, I enjoy talking to people and hope it works both ways. The topic is about the torus action, so we'll have another talk about the group action. Most actually talks that I heard. Yes, they had some group action in the background. And my collaborators in this project were Jarek Wisniewski and and I should thank a number of people to whom I talk on this, including Klaus Allen. So let me think if I can handle this. All right. So as the headline, I wanted to choose the title of Katz article in 1966 in American Mathematical Monthly. So the title is, as you can see, so suppose that you have an instrument and you want to know its shape by the sound it makes. So in other words, you want to analyze frequencies. So in terms of algebraic geometry, it's studying the varieties in terms of the action and actually in terms of the eigenvalues and the eigenspaces of the action somewhere. Okay? And essentially the talk will be divided in two parts. So the first part is about the methods, and then the second part is about the results which would be proved with this method. And the results are presented in this motivation slide. So there is this theorem, or rather two theorems, one by de Rham and the other by Berger, in Riemannian holonomy. So in case you just forgot what's the holonomy, so you have a Riemannian manifold, you make a parallel transport, say simply connected for simplicity, you make a parallel transport of a vector along the loop, then you come back to the same point, and so you have some transformation of the tangent space. And then it turns out that the groups generated by this transportation fit in only in the number of several patterns. One of them are quaternion-Kähler manifolds, and then if you, one of the cases which is not worked out for a long time now, is the Lagrange-Salomon conjecture that all of these that have this special group holonomy are symmetric. In terms of algebraic geometry, you can, using the construction of, I think to whom should I attribute, I mean the, okay. At any rate, you can pass the same problem to the complex geometry case, and then you can restate it in terms of the contact structure on the Fano manifolds. So if you take a Fano manifold, then the conjecture says that it makes a complex contact structure only if it's homogeneous. And actually, this is a projectivization of the minimal adjoint orbit of the action of a simple group. Okay. So that's the motivation. And now about the business. I should first explain what was the contact structure. So this slide somehow makes it explicit. So the contact structure is a codimensional one sub-bundle with a quotient which is line bundle, and then this is somehow completely non-integrable, so that if you take the Lie bracket on the vector fields here, then the values will be here, and it will be never degenerate. So in particular, you can make it algebraic in the case of a complex compact manifold. Then this says that you have the form theta, so this is the morphism associated to the form, and then if you take its derivative, then wedged with the with theta is nowhere vanishing. So in particular, it also determines the relation of this line bundle L with the anti-canonical. This is explained over there. Okay, and also this Lie bracket defines this Q symmetric pairing on this bundle F with values in L. We will use it later. I mean, I think that most of this is standard, in a standard course in mechanics. I mean, you talk about the symplectic structure, then you talk about the contact structure. And as far as the results regarding the Brown-Salomon conjecture go, there are several ones. In low dimensions are due to the Hitchin pool, and also the Brown-Salomon, they actually swept out some cases. Then there was a result by Herrera and Herrera in dimension 7, which turned out to be, well, the proof turned out to have some problems. There were the results. A number of people, essentially, if you go to the dimension-wise, everything is known up to dimension 5. So the contact phenomena manifolds in dimension 5 are up to 5 are known. And then there are two cases which are solved actually based on the knowledge of Fano manifolds, and it was observed by LeBron and Salomon that if the Picard group is not generated by this line bundle L, so if L is divisible, then we have the contact structure on the odd dimensional projective space, and if the Picard group is not one-dimensional, then there is a result of 4 authors, Kevicus, Peter, Somers, and myself, which says that this is the projectivization of the tangent bundle and in the panel case it has the projective space. Okay, so that was the introduction, and now I want to talk about the method. So I will talk about the case when we have a torus, which will be always denoted by H, and R will be the rank of the torus. So this H will be that C star to R, and this H is equipped with the 2 lattices. I mean, this is the standard thing that you teach in or learn in a course of toric geometry, that you have this lattice of monoids, so these are the characters of this torus, and the dual lattice, which you can identify with one parameter samples. And then you say, okay, if you want to understand a toric variety, say, suppose that L is ample over a toric variety X, then this is the same as to draw or construct a polygon in the lattice MR, I mean actually in the space MR. Then you look at the lattice points inside. Then the lattice points inside are eigenweights, for maybe I reveal this slide totally. So the lattice points here are the eigenvalues of the action of the torus on the space of sections of this L. So what sits inside is H0 of S and L, but divided neatly in one-dimensional eigenspaces. And moreover, you can either describe this variety in terms of the dual objects in the space of N, so you can construct a normal fan, or you can think about say, the complex associated to this polytope and define the ideals associated to the faces of this polytope. In other words, you can take extend this picture to one-dimensional more space. So this is say 1 times m, and you take the z times m lattice, and you can construct the high-dimensional sections of this L, put everything here, and then you can, for example, take the ideal of points which don't lie on the edge of this polytope, on the ray, which comes from the vertex of this polytope. And this will be, it turns out to be the idea of the fixed point of the torus action. So essentially, everything is just described easily. In particular, as it's noted on this slide, the fixed points of this action can be pictured as the vertices of this polytope. Actually, if you think about this, if L is ample, then you can use the apparatus of the moment map to describe these objects. So now, what I want to do is to consider the case when this torus H acts on a variety of a bigger dimension, so that actually we don't have the dense orbit. Okay. So I will assume that H acts effectively on a projective variety X equipped with an ample line bundle L, and I will assume that the line bundle admits a linearization, and here is a star with this effectively. By effectively, I understand that the kernel of this action is at most finite. Okay, so in particular, I don't want to have a one-dimensional subgroup which are trivial. Okay, then one thing which you can see is that the same idea, because of the linearization, the same idea of the composition of the space of section into the eigenspaces associated to the characters, to the weights of this action, works. Okay, so you have the decomposition. The only problem is that now possibly the dimension of these spaces here are bigger. But even worse, you may have the situation which does not occur when X is smooth, and actually I will almost always assume that it is smooth, that this thing can be empty. So you don't have anything. I mean, it may happen equally well. Okay. Nevertheless, for a given L, I will distinguish, well, the set of, well, I chose the linearization, right? So I have a quadruple X, H, L, and mu, and you can define the set of points which are the eigen values of this action on this set of sections. And mimicking this construction, I would like to also to define the polytope, which is the convex hull of this. And I will call these objects the gamma tilde and gamma. Okay? So that's one side of the story. The other side of the story is that I'm looking at the fixed point set of this action. Then it turns out that it decomposes into a finite number of components, and since I want to assume that X is smooth, by the lunar slice theorem, they will be just smooth subvarieties. Okay, and now, if I take each of these components, okay, so I take over this component, the action of the torus with the given linearization is provided by some characters. I mean, you don't move the point, you just act by the character over the point on the fiber of the line. Okay? So given the linearization, I can distinguish the number of the eigenvalues associated to the action on each of the fixed points, and of course it's clear to see that on a given component you will have the same eigenvalues. And again, I define this time a polytope, which I will call delta, which is the convex hull of these. And now I will distinguish some of the components. I will call the component extremo if it is associated to the vertex of this polytope delta. Okay? Now there are few easy observations. So the first observation is that if I multiply L, then this, the multiple will have, okay, as you see at the very beginning, I use the notation of the four element data, the variety, the torus, the line bundle, and the linearization. Whenever it comes to the details, I will assume that, of course, that the variety and the torus are given, and the linearization, okay, in particular case of the multiple, I'm just taking a natural linearization coming from the linearization on L. Then, clearly, the polytope, I mean, the eigenspaces will be just, eigenvalues will be just multiplied, and we will have this polytope expand. On the other hand, this is also obvious. I mean, if you multiply sections, then the eigensections of this action, then there will be also eigensections, and the characters will add. Then the next observation is almost equally.
But it could be that delta of L is empty while delta of L...
No. Delta is not empty because it has fixed points. So delta are fixed points and gammas are sections. So I agree that it may happen that this part is empty, okay? But still it's true, okay? So, now the next observation is also, in some sense, it's more or less obvious, if you look at it. If this is, if L is base point free, and so in particular, suppose that you have a point which is a component Ly, then you have this sequence, and in particular this is surjective. On this it acts the torus H, and it acts by the linearization. And remember that here we have the compatible linearization of the action on the total space and the linearization on the space of sections. Therefore this is equivariant map, okay, so in particular it splits, okay? So in particular among the eigenvalues of the action over here, I'm supposed to have the eigenvalue which comes from the action over this fixed point component. So this implies the inclusion, let's see, in this direction. What's here lives here. The inclusion in the other direction, I essentially explained when I discussed the case of toric varieties. If you take the ray, okay, then you can, if you take a ray here, then you can define an invariant subvariety, an ideal of an invariant subvariety, okay? You just take the sections which have the eigenvalues which are not contained in the ray, okay? And this is additively closed, therefore it defines an ideal. And the action over a closed subvariety must contain fixed points. So inside you are supposed to have the fixed point components which have the eigenvalues associated to the ray in this data. So in general, if you think like asymptotically, these two things are supposed to be the same. Okay? So look. A priori, we are not in the toric case where they were from the very first step they were the same, but asymptotically they are the same. And also we know that we have the I think that's the if I have this I just wonder if I have the right inclusion. Yes. Since I have the inclusion here, I always have the inclusion in this direction. Okay? All right. So the idea is that if you don't hear too many sounds, so if you know that there is a finite number of a small number of eigenvalues, and you can somehow hear all these fixed point components associated to this eigenvalue, then probably you can rebuild the whole variety. That's the whole idea. Okay? And we are missing one more one more component in this toric description. So the component in the toric description is the dual fact. If you look at this polygon which I erased, okay, so this is the vertex of this polygon, then you say, all right, this is the fixed point component, but this cone here, moved neatly to the center, is actually the cone of the coordinates of the invariant neighborhood of this point, invariant toric neighborhood. Because the dual cone to this cone is the cone in the fact. So this is the cone in the neighborhood. Okay? And actually then, the other thing which you know, that if the variety is smooth, is that the cone is the regular cone. So it's not only simple issue, but the rays are generated, actually the semi-group of the points here is generated by the primitive vectors on the edges of this cone. Okay, so we will try to mimic this. So let's take a connected component of this torus action, and then let's fix a point, okay? Then we have a split, okay, again, by the lunar slice theorem, we can split it, the action on the tangent space, and by the étale lunar slice theorem. Actually, in étale topology, we more or less understand how the action in the neighborhood of this point looks like. Okay. In particular, we have the split on the trivial part, which is the tangent to this fixed point set, and you have the other direction. So the eigenvalues, okay, the next part of this, the non-zero eigenvalues, I will call the compass, but for technical reasons, I'm not taking the tangent space, but the cotangent space. And you will definitely know why. Because if you take the toric case, okay, so that's the general toric case, okay, so that's the angle, which is a part of this huge polygon, which you remember, but from this angle I just construct the cone. And okay, so these are the coordinates, these are the primitive vectors, and actually in my language, these are the elements of the compass. Okay? These are the eigenvectors, these are the eigenvalues of the action of the torus on the tangent space. Why is that? Because, come on, in the toric case, you just write this invariant neighborhood in the smooth case as just a fine space, and these are associated to the coordinates of the eigenspace. Okay? So the vectors from here to here are actually the characters on which the torus acts on these eigenvectors, so in this coordinate system. Okay? So, yeah?
Where do you call it a compass?
Because I want to sound romantic. No, well, maybe if we go, okay, all right, so now be less romantic. I will have more slides like this, just in a moment, but essentially, if you have this point, okay, then if you have the compass, then you can think about so it defines the direction. So you can consider the eigen curve associated to this direction. So in some sense, these are the principal directions in which you have the curves associated to the action, the distribution of these curves. I will try to explain it later. All right. Then the next observation comes more or less from this setup, this toric setup, okay? So what I'm saying is that if you have the elements of the compass, you move the polygon so that the vertex becomes zero, you span the cone, and inside this cone, we consider the eigen sections of multiple of this line bundle, then it will be semigroup. But then this semigroup will be generated by the elements of the compass. I know that it sounds funny, But a quick argument is as follows. I mean, locally around, so we have this point y, which lives in a fixed point component y, okay? And then you have this ly, and say with the invariant psi coordinate, okay? Then take a section, say sigma, in h0 xl associated to the character u. Okay, so locally you present this section as some polynomial times this psi. That's the representation of this. And now on this you have the eigenspace, the eigenvalue here is called q. The eigenvalue here is called mu of this component ui. Okay? So the difference between these will be the degree of this polynomial, but seen as a character in this lattice M. And if you have the eigenvectors of the action on the cotangent space, then this is exactly the degree which will be obtained if you write this polynomial, either in the étale coordinates or in the formal coordinates. Then actually you write this polynomial in terms of these eigenfunctions, okay? And the eigenfunctions have the eigenvalues which sit in the compass, right? So every section after normalizing, so after subtracting the character associated to the fixed point component, or shifting the whole polytope so that this vertex becomes or more generally, not necessarily vertex, but the eigenvalue associated to this fixed point component becomes the center. Every section is written as some polynomial whose degree is described in terms of the elements of the compass. Okay, so that's this first remark. Okay, and now two constructions which are important. Because, all right, intuitively, the bigger torus you have, the more information you should gain. But how to do it? Well, usually, if you want to construct a general theory, you want to somehow to make the reduction of the action to a smaller torus, or okay, let's see how it works. Okay, so take the subtorus and take a short exact sequence of tori and the associated sequence of the lattice of characters. Okay, so if you take the restriction to a subtorus, then you will call it the downgrading of the action. Like you have a toric variety, then you downgrade it. That is, you just look at the subtori of this action. Then you want to make possibly examples of varieties which are non-toric, but okay. So the downgrading is one option, but if you downgrade it and you take the fixed point set, then still the quotient torus will act on the fixed point set of this smaller torus. So somehow you decompose the action of the bigger torus into the action of the smaller torus, and then the action of the quotient torus on the varieties. And actually, on each of these components, the components of this quotient torus, of the fixed point set of the quotient torus, are the components of the original torus intersected with the fixed point component of the smaller torus. If you think about it, then you will see that this is obvious. Okay, and then there is, say, some natural mantra. Okay, so first of all, we have this projection of the lattices. Okay. So the construction is natural. So if you take the downgrading, so you have the projection of lattices associated to the subtorus sitting in the torus, then all the construction is associated to the map of the lattices, right? I mean, what the last 15 minutes, I've been trying to translate the vision of a variety into the vision of a discrete set sitting in a lattice, okay? Then what I'm trying to say is that this construction is, if you look at this properly, is functorial. That is, if you take a subtorus and you do the same construction, then this is the same as just brutally take the information from the big torus and just project it down to the subtorus, right? To the lattice associated with the subtorus. But this concerns the polytopes, the eigenvalues, and this concerns also the compasses. So, in particular, if I'm taking the projection associated to a vector of the compass, this means that the eigenvector associated to this eigenvalue along which I'm projecting will be killed, which means that the torus to which I project, or rather the subtorus associated to the projection, will act trivially along this vector. Okay, so the fixed point set will be bigger. Okay, let's do the examples, because this is exactly the point when everyone thinks, okay, I'm doing here kind of. Okay, let's take the first variety, which is not a toric variety, which is the quadrant, right? And if you go to dimension 3, then the first, and you teach a course about the toric variety, and then you try to explain to the students that the variety is different from toric varieties, then you are stonewalled by the example of the quadric, which is easy, but okay, so that's the standard action, okay? You take the action, I start with the odd dimensional quadric, on the first coordinate 0 and then plus minus 1, okay? Okay, the next two are easy. So the equation of quadric is preserved and the fixed point set on the projective space, there are two n of them. Okay, everybody knows it. How does it look from my point of view? I want to understand the torus action, so I'm taking the lattice of characters of this torus, and I'm taking L. Of course, the L will be the O of 1, the restriction of the hyperplane section to the. Then, what will be the polytope? The polytope will be the convex hull of plus minus 1s, which were the characters associated to the action on the coordinates. So this is not an accident, right? Then, if you go to the compass, then you are supposed to understand what will be the derivative of this. Then it turns out, okay, let me show you the picture. So that's the first case of a three-dimensional quadric, which is not a toric variety. We have 5 sections, 4 fixed points, which are the full dots, and if I take one full dot, then the compass is exactly the 3 arrows coming from here to here. And if I take the cone of the sections of the multiples of L, then clearly the compass generates all. Let's do the next. I'm skipping now. Even-dimensional quadric. Good. Same thing. The only difference is that now there is a finite subgroup in this torus, and the multiplication by minus 1 acts trivially. Okay? And that's the 4-dimensional quadric with the 3-dimensional torus action. Okay? And actually this is the compass.
Isn't it strange that the cones are not simplicial?
It would be strange if they were. Because the point is that, of course, the compass has okay, if the fixed points are isolated, then the compass is supposed to have as many arrows as the dimension of the variety. Okay? And then, of course, the dimension of the torus, you want to assume that it is smaller. Okay? So the compasses are usually bigger than the dimension. And here, which is not the accident, and I'll try to explain it in the next slide, which is rather a rule, there are no inner vectors in the top. So just an accident that you don't have an inner vector. Okay, and now the downgrading. This is the same situation, and I want to explain the downgrading. What I'm doing here. I have this lattice which is generated by the eigenvalues of this action, and now I'm taking, you see, this is octahedron, right? That's the name. And now I'm taking projections so that this face and this face are contracted via the projection to a one-dimensional lattice. Okay? I can do it, right? Everybody sees that I can do it. And this is the reduction to one-dimensional group action. And now, as you see, I have two fibers. This is the front wall and the rear wall here. And on these, I have the action of two-dimensional torus. And you see that these are the quadrics. If you write down the equations of invariant subset with respect to the action, actually you can choose, say, the diagonal action in this three-dimensional torus. You take the diagonal torus, and this will be exactly the example in which you will have the two faces, I mean, two fixed point components, this one and this one. So that's the whole idea. And now, say, I promise that I want to prove a theorem about homogeneous spaces. So actually, a part of the downgrading of the torus action from the toric varieties, you have a very natural class of varieties on which you have the torus action, namely the homogeneous varieties and with the maximal torus. Okay? And voila, this is an example of such. I'm taking the B3 root system, which turns out to be one of these bad guys, which in the end you are supposed to work on very hardly to have them done. And so, what's the B3 root system? These are the same as the weights of the maximal torus action, the Cartan torus action, on the adjoint representation. Well, except that I'm supposed, but I didn't do it, inside I have the point inside, which is associated to the Cartan subtorus. Are you with me? I mean, I'm trying now, despite the fact, as Miles did, I'm trying now to shed the light from the point of view of the representation theory. So here I have the B3 root system, and amazingly, this is what we get. Namely, now the picture is as follows. It turns out that if I take the joint representation and I take the minimal minimal nilpotent orbit of this joint representation action, then it has the fixed point set is described by these full dots. Then the eigenvalues are described by the full dots of these dots, which are the intercenters of the faces of this cut cube, and the compass looks like this. Okay, what should I say here? There's certain symmetry in this compass. Because now the important thing is that maybe I should make a two-step argument. Okay? The first one is that what is the compass? Actually, the compass is the same procedure of making the linearization, but on the action of h, on the tangent space at the fixed point. Well, I have a natural linearization coming with the differential of the action, right? And then I have the decomposition of this space into the eigenvalues, eigenspaces, and now I'm not throwing one value, but I'm throwing a number of eigenvalues, and these are actually the eigenvalues which make the compass. Well, for example, you may wonder what you will get if you take L link minus kx. So you take the I'll take a manifold. So remember that this is the wedge of Tx. So what will happen? The polytope which you will construct will have this very nice feature that remember here I'm considering a very special linearization coming with the differential of the action, right? So the polytope will be given once and for all. I can forget about talking about the linearization, which possibly could shift the polytope. But each of the vertices will lie on the point which will be just the sum of elements in the compass. Why is that? Because this is the wedge product of Tx with minus. So here, for example, you see a very nice feature that if you take the pair that you have these elements in the compass which come into pairs, and each of these pairs adds to this red one. Okay. And this is essentially the main idea, but I should notice that you have the downgrading procedure.
So, I'm sorry, the variety...
Go back.
The variety in this example is the flag variety of type B3, is it?
No, this is the variety of lines on the six-dimensional quadric, and you can see this face is...
Why is this dimensional B3? Five-dimensional.
Maybe five-dimensional. Yes, you're right. I'm sorry, five-dimensional. You are perfectly right. Yes, and now explain how can you see that it's five-dimensional. You have this face, right? If you take the downgrading which projects it down, this will be a fixed point set of this, which, as you see, is a three-dimensional quadric. Because we saw it just in the previous slide that it is a three-dimensional quadric. Okay? And this three-dimensional quadric is associated to lines which pass through a fixed point of the action on five-dimensional quadric. Okay? So I consider it enlightening that looking at these pictures, you can actually see the structure of the variety. Okay, and here the downgrading. One downgrading was shown, the other downgrading is somehow slightly non-obvious. Namely, you can take the slice of this previous polytope so that it looks like a hexagon, and then you can take the projection somehow orthogonal to this one. Okay? Then you see that the result will be a hexagon with another hexagon inside. Or you can take the other downgrading, that is now you take the projection along this green to one-dimensional space, and then you will see that the decomposition of the fixed point set of this one-dimensional group action consists here, the isolated fixed points, then I have P1 cross P1 and two green planes, and then I have P1 inside. So you can see that, all right, good. So these were the examples. And now the main tool. The main tool is called Wisniewski visual decomposition. Because so far we tried to establish some theory based on, well, okay, there is no information to be fed in. So now I'm trying to provide you with a tool which allows to get the information from the variety itself. And it's called Wisniewski visual decomposition. I'll let it load. So suppose that I have the one-dimensional group action. Then I do what I did before. So I take the decomposition into the fixed points. And then for every of these fixed points, the compass is now very poor, okay? So either the positive components or negative components. I mean, the disadvantage of one-dimensional case is that it's one-dimensional, so you can't do any downgrading anymore, right? You can't play with what I try to play. But the good thing is that we know what's on the right and what's on the left, okay? That's the feature of, okay. So, for every of these components, by this mu, you denote the number of the positive and the negative elements in the compass, and then you define the Jarek-Wisniewski cells, the positive cells and the negative cells. The idea is essentially like this, that again, the one-dimensional torus has one direction and the other direction. So now you take just a point at the variety, and if you want to have the positive cell, then you let it flow, and eventually the closure of the orbit defined by this point will hit some fixed point, okay? Then I say that if I fix a component, yi, then I'm taking all these points, and this is the class decomposition, which with the positive flow will hit this component, okay? And theorem says that this is the decomposition, right? So actually it has nice, these are locally closed, algebraic, etc. What you want, you have a partial order, first of all, associated to the closure. And what is more, now the important part, here in the assumptions I didn't make any mentioning of this L. But if I assume that I have an ample L, then this partial order, the order is that in the bigger component consists of those points which are in the closure of the other component, right? Then this agrees with this order determined by the linearization of an ample line bundle. And to check it, you just check it for the projective space, and you see again by the functoriality that they exist. And there is the important part is, if you have this polytope, which is one-dimensional, then you have two distinguished points. The two distinguished points in our previous language, they were called extremal components. In this language of Wisniewski-Birula, they are called the source and the sink. And they have this very nice feature that depending on the direction of the order, either the cell will consist of one point, or the cell will be dominating. Actually, well, one point, the fixed point, the cell will consist of the fixed point component, or it will be dense in the all variety. Okay? All right, and based on this, you have the decomposition of homology. It comes from this cell decomposition and from these properties that each cell is actually a torus bundle, a vibration over this. Now I want to consider the case when you see, guys, the problem is that I don't have my watch, so I will continue.
10 minutes.
No kidding. Okay. Good. All right. So if the Picard group is, that's when the Mori theory actually fails. You have a smooth variety. The Picard group is one-dimensional, and what will you do? There is nothing that you can contract. Okay? That's one of the problems. Here, on the other hand, the situation is just perfect. Because if the Picard group, and you have, say, one-dimensional torus with the source, then first of all, X is fundamental. This is obvious, because Picard is one-dimensional, it contains many rational curves, no problem with this. But then, if the source is positive dimensional, it's also final, and because of the decomposition of the cohomology, it's again of the same nature, right? And the complement of this component is of codimension 2. So in particular, the restriction of sections is surjective. Because you lift every section from this component to its neighborhood, which is dense, the complement is of codimension 2, then you are good, okay? And a similar thing, if this is a point, here you know that the complement is the irreducible divisor, which is actually in this linear system. again comes from the cohomology. And moreover, if this is a single point, then still you can derive even more information. Namely, since the Picard group is Z, there exists the next one. The next one which will contribute to the second cohomology, and this is the source for the divisor, for the generated divisor. Okay? What comes with this? Okay. Now we pass to the case when the rank is higher than 1, and you are good. Namely, the vertices are potential sources or sinks for the one-dimensional group action. So they have the very good properties. And the extension property, which I tried to explain, tells you just a slide ago. A slide ago I said that you have the surjectivity here, and also this is a point and the complement is the divisor and the generator. Okay? So now it reads that these two politons are the same. If the rank is sufficiently big. Essentially, it follows from the fact that we know that Fano threefolds of the first species, they have the section. The generator has a section. So by the downgrading procedure, if the rank is big or equal than 4, this extra one comes from the fact that okay, let me not explain. Well, I mean, by taking the faces, I can make the inductive argument, and using at the bottom of this the fact that three-dimensional Fanos, or smaller Fanos, have section, that the generator has section, I have this thing. Okay, so essentially now the idea should be, if you know that the torus is sufficiently big, then go ahead. If you know what are the sections and what are the eigenvalues of the sections of the generator, probably you can rebuild the variety. And now the application, which is the main theorem, but before this I will recall Atiyah-Bott, Grothendieck, Atiyah-Bott, Berlin-Bernin localization of homology. Whatever it is, the important part is the corollary. The corollary says that if I have a simple, or actually semi-simple group acting on a variety, and the big torus has exactly the same set of points and the set of compasses as for the homogeneous, for a homogeneous variety with respect to this group, then these two varieties are the same. Because the proof is almost immediate, because this formula says, these big guys formula says that no, if the points are isolated, okay, so that's in our assumption, if you know the compass, these are the elements in the compass, then you can recover the generating functions for the characters in the big torus representation in the simple group. And then one of the standard facts in the representation theory is that the representation of a semi-simple group is actually determined by the characters of the big torus action. So you have two representations on the, well, you may assume, of course, passing to sufficiently large multiplicity of that it is variable. So you have two representations on the vector space, and of course both varieties, this guy which you don't know and this guy which you know, are invariant. They have the same dimension, and this is the unique closed orbit, therefore they are the same.
So there is a unique closed orbit when the representation is reducible.
Yeah, but I know it because
You know what?
I know it because for x hat, I know this guy, okay? The x hat is known. Therefore, the representation, if it has the same characters, then, okay, then it's irreducible. Okay, I'm sorry. These are the two theorems which I want to prove. Okay, so essentially the second one proves the Lebrun Salomon conjecture up to dimension, let me see. Because this is the real dimension, so it's always a problem when multiplying by 2, then adding the twistor dimension or whatever. Yeah, I mean, the next two steps are done, okay?
Mhm.
Okay, and the proof. The proof is as follows. So we look at the sequence which I explained, then the point is, and this is the classical observation, that if you take the group of the contact automorphisms, whatever it is, it may be empty. Yeah? But at any rate, you can identify the sections of L, maybe none, with the Lie algebra of this group of G, and G acts via the standard representation coming from Tx on this H0, like it acts on G via the adjoint representation. Okay, so that's one observation. So in some sense, if we can shrink and our assumption to the case that we know that G exists and is non-empty, then we have at least something to grip on, right? And then the next observation is a trivial observation that if you have this contact form, the derivative of this contact form, it defines the bilinear pairing. So in particular, it defines lots of symmetries in the compass. Namely, I can renumber the values in the compass so that they will add to the, if I have a more problem, if I have a fixed point component y, then taking the values in the compass, I can renumber them so that one of them is the one associated to this guy, actually with the minus sign, sorry, but I know this way, and the pairing, this pairing, will imply that they will come in pairs so that they add to this guy.
And the minus sign is because you consider quadrant?
Yeah, yes. The minus sign. Okay, and there are two corollaries. The first observation is, if I take the component and this linearization is non-zero, then this is isotropic. Essentially, because this pairing takes everything to something which is positive, right? And if it's zero, then this component actually is contact. If I restrict the contact form to this one, then it's just contact. Okay, now the sketch of the proof. I will put all the 4 points. Okay, the point 1, I said that in arbitrary case, not necessarily Fermat contact, if I know that the rank of the torus is sufficiently big, then I can make this equality because I know that at the extremal fixed point components I have a section. Now, in addition, I know that the extremal fixed point components are isotropic. So their dimension is actually by one smaller of one. If the dimension of this contact variety is 2n plus 1, then they are of dimension 2n, right? So by this inductive procedure of extending the sections, I'm actually landing in the situation in which I can, for every extremal component, I can produce a section. Remember that my theorem assumes something about the rank of the torus. That's the assumption. So using this assumption, I come to the conclusion that for the extremal components, I can produce a section on them, and therefore I can extend them to the section on X. And therefore these two polytopes are. The other thing is, okay, remember that this polytope was associated with the adjoint action of this group, reductive group. The reductive was in there. Okay? So the reductive group is a torus times semi-simple. Okay? But the adjoint action on the torus part is trivial. Okay? So it's impossible because we assume that the action of the torus is actually non-trivial. Therefore, the group is semi-simple, does not have the torus component. The next reduction is to the simple case, essentially because if it's simple, then this is the product of the root polytopes. A root polytope is a polytope which is spanned by the roots in the space of the weights of the simple group. And then you just verify. I don't want to get into the details, but essentially it's well, we reduce to the simple case, and then we have the case-by-case analysis, and I try to tell you why this is the case. Okay, so here is the dimension of the joint orbit for each of these groups, right? Then, incidentally, in most of these cases, if you take the polytope, the root polytope, then in the unlaced cases, if you look at the classification of the simple Lie plus or Lie group, then there are two cases which are somehow behave slightly different. They are unlaced, so these are the Dynkin diagrams without multiple edges, right?
You mean simply laced?
Oh, I'm sorry. Unless you can have the shoes, right? Sorry, simply laced. Yes. Okay, so in the simple laced, you don't have short roots. So actually your polytope is generated by the, inside the possible weights to which you can associate the, I'm sorry, maybe I'll make it short. In the simply laced case, the compass is generated by the edges.
The polytope is strictly convex.
The polytope is, by definition, I don't understand what's strictly convex.
There is no vertex on a face.
There is no vertex on a face. So the number of the edges coming from the point is exactly as many as you are supposed to have. So if you go, say, all these nasty cases are done because they have many edges. Well, here, this is the Dynkin diagram so you are supposed to work a bit more, but the same argument works. Then in the case AR, actually is associated to the projective space. No, I'm sorry, not to the projective space, but to the projectivization of the tangent of the projective space. And you can see it from the root polytope. Okay, in the low dimensions, it's not obvious, but in the high dimensions from dimension 3 on, you see that you have the faces which are associated to the varieties which have the B2 equal to. Okay, the C case is associated with the projective space. And this is the situation when this L is divisible by 2. And you can see it from the root polytope as well. So essentially you are supposed to deal with the B and D cases or with the low dimensional cases. And I will skip because I prepared more slides explaining how to deal with the small dimensional cases, because it turns out, well, so this is, for example, I will just make an animated movie how to deal, say, with the 7-dimensional case with the possible group of type A2 or G2 acting. So essentially the analysis is that first you look at the possible compasses. Okay, so external points are of this type, internal points are possibly of this type. Okay, this is possible distribution, and then you take the restriction to, you take the downgrading and you try to understand what would be the possible fixed point components for the downgraded action. And it turns out, amazingly, that the only situation that comes out is the one which comes from the projection of the B3 root system, okay? Which is very nice, okay? And I think that I already stretched your patience, so I think I'm done. Okay, thank you.
Questions? Comments?
What will be the next step?
Well, okay, so thank you very much for the question. This is a very good question because I can praise all this program, which is a great idea for possible extensions. I think that there are several paths. Okay, the first path, as far as the contact goes, then you can try to extend this. But this is, I think, convincing example that this possible extension of the toric geometry for the non-toric case may work, okay? But there are several things which are true in the toric case, very well understood. As I, for example, told you, bacteria have had this reflexive polydopes. You don't have the reflexive, but you have a very nice class. Well, they are not actually polydopes. I call them grids, because they are coming. So, okay, I will draw a grid. So you saw a grid of, so this picture describes the fixed points that are here, and not only describes the compasses, but also describes the orbits. Essentially, if you extend the orbit, it's supposed to hit another fixed point, right? Then you may think about the classification, for example, of Fanon grids, smooth Fanon grids in higher dimensions. Okay? The other possibility is there any natural notion of doing mirror symmetry business within grids, not within the polydopes? That's another question. I think that this is I don't, there's not much contents in terms that at each, say, of these observations we went epsilon behind the toric case. But the result, as I tried to present it, is pretty new. I mean, you obtain the classification of varieties on which the torus is sufficiently small, right? But yet you have enough information, and using all these business, you can get something. So I believe that this is worthwhile to look at. If this answers your question.
And is there some relation of this with the theory of spherical varieties?
Definitely yes, but I don't know.
Single case.
That's also a perfect question. I don't know. The first notion makes sense, but then I think if you think about the quotients singularities, a good class of singularities, then maybe you can make out sense for the compass. What compass would be? The compass in terms of the orbifold or something like this. Because this is like a toolbox, right? I mean, like in toric varieties. In toric varieties, everything comes nicely packed and already fits. Here, well, the things are adapted, so of course it does not fit, at least in the first attempt, but maybe you can adjust them so that they do.
More questions? If not, let's thank Jarek again.